let's talk about something fundamental to all programming, the finite canvas and specifically a compiler's guide to data type limits.
Hello, I am the compiler. I'm the one who translates your human ideas into the raw language of the machine. But today, we're doing something a little different. I'm letting you look under my hood to see the very edges of my world. So you want to know the range of data types. It sounds like a simple request, right? A list of numbers to memorize. But to me, it's not about that at all. It's a much deeper question. It's really a question of space and geometry. Here's the essential problem we always have to solve. In the world of pure math, numbers go on forever. They're infinite. But me, I live inside a computer. I am finite. I have a limited amount of memory to work with, a finite canvas. And every single variable you create has to be carved out of that physical space. So what happens when you try to cram an infinite idea onto a finite canvas? You get this, overflow. Imagine you have a small cup, and you try to pour a whole gallon of water into it. It's going to spill everywhere, right? Make a huge mess. It's the same exact thing with numbers. If you try to store a value that's too big for the space I've allocated, it spills out, corrupting your byte data and causing all sorts of chaos. And that is why these limits matter so much. So how do I build these little containers for your numbers anyway? Well, it all starts right here. Every single piece of data, I don't care if it's an integer, a character, anything, is ultimately stored in a box of bits. And a bit is the smallest possible unit of information you can have, just a 0 or a 1, an on switch or an off switch. That's it. We usually group these bits into a standard-sized box of 8, and we call that a byte. You can think of a byte as the universal Lego brick of data. Everything from numbers and letters to images and sounds, the whole shebang, is built from these fundamental blocks. And watch what happens when we start putting these bits together. The capacity grows incredibly fast. As you can see, one bit gives you just 2 options. But add a second bit, and you double that to 4 possible combinations. By the time you get to a full byte of 8 bits, that exponential growth gives you 2 to the power of 8. That's 256 different values you can represent. This power of 2 is the key to everything. Okay, 256 values. That's great. But so far we've only been talking about positive numbers, just counting up from 0. What happens when you need to represent something like debt or a temperature that's below freezing? I mean, what about negative numbers? And this brings us to a crucial decision, a fork in the road that I call the Great Divide. On one hand, we have unsigned types. Here, every single bit is used to represent the size of the number. This gives you the biggest possible positive value, but no negatives allowed. On the other hand, we have signed types. For these, I do something clever. I reserve the very first bit to act as a signpost. It tells me if the number is positive or negative. This lets you represent the negatives, but here's the trade-off. You just cut your maximum positive range in half. Now pay close attention, because this right here, this is a golden point. Understanding this sign-bit trade-off is the single most critical concept for grasping why data type ranges are the way they are. You are always choosing. Do you want a bigger positive range, or do you want the ability to represent negative numbers? You can't have both at the same time. Let's make this totally concrete with our 8-bit byte. Remember, it has 256 possible patterns. For an unsigned char, we use all 256 of those patterns for positive values. Simple enough. That gives us a range from 0 to 255. But for a signed char, we have to split those 256 combinations down the middle. We use half for negative numbers and half for positive. The result? A range from negative 128 all the way up to positive 127. Same number of combinations, just divided up differently. Okay, so you're starting to see the logic. And I know what you might be tempted to do now. Make a bunch of flashcards and memorize the exact ranges for int, long, short, and all the others. Let me tell you directly. Do not do that. It's a complete trap. And here is exactly why memorizing is such a bad idea. The meaning of a data type like int isn't universal. It can change depending on the machine. On a small 16-bit Arduino controller, the maximum integer you can store is about 32,000. But on your modern 64-bit laptop, that same int can hold a value over 2 times billion. If you write code assuming one size, it'll completely break when I compile it on a different machine. That's the portability problem. So what's the professional way to handle this? Well, instead of guessing or memorizing, you should consult my official documentation, my built-in system manuals. In the C language, we call these the header files. There are two main rulebooks you need to know. First is limits.h. This file contains special definitions, or macros, for all the integer limits, like int max. The second is float.h, which, you guessed it, does the same thing for floating point numbers. When you use these macros in your code, I automatically substitute the correct value for whatever machine you're running on. Your code becomes portable and correct. Every time. So the trick is connecting the right tool to the right job. This table right here is your map. It shows the data type, the macro to find its limit, and, this is critical, the correct format specifier to print it. A specifier like %d or %u is just a code that tells the print function how to display a variable. Using the wrong one is like using the wrong key for a lock. It just won't work and you'll get garbage output.
Let's just put this all together into a simple blueprint for success. First, always include my rulebooks. Second, always use the macros like int max to get the boundaries. Never hardcode the numbers. Third, be meticulous and match the format specifier to the data type, like using %LLD for a long. And finally, remember that for floating point types, you'll often want to use %e for scientific notation.
Let me save you some future headaches by pointing out the mistakes I see all the time. The most common one? Using the wrong specifier, like trying to print a huge long with a simple %d. I'll just end up printing nonsense. Another big one is hard coding limits. That's a portability nightmare just waiting to happen. And here's a subtle one, forgetting the capital L in %LE when you're printing a long double. Without it, you're not seeing the number's full precision. So you now understand the finite canvas, at least for integers. But there's a deeper mystery here. If you look up the limits for a floating point number, why is its minimum value a very small positive number and not a large negative one like an integer? The answer lies in the strange and fascinating geometry of how I store decimal numbers. But that is a story for another time.